Okay, thank you very much for the invitation. My name is Helmut Hlavacs. I'm professor for computer science at the University of Vienna. Today I will talk about our teaching courses on video games, video game technology mostly. We have similar interests with Günther Wallner, who I know have been known for a very long time. So we share this common interest. So I thought it makes sense to tell you about how we teach, or what we teach, and how we teach that. So our faculty is situated in this building in Vienna. As Karen said, I'm heading the research group, Education, Didactics, and Entertainment Computing. We are the entertainment computing part of that, but we have many other research groups. So the faculty is growing, and we have this rather new building also. So this is our department, and we offer, of course, a couple of studies, bachelor, master, and PhD level studies. The bachelor studies are in German, as it has to be according to the law, but the master studies are all in English, and that means that we have a rather international mix of students in our master studies coming from the East, for instance, Eastern Europe, Erasmus exchange students. And here we have also various master studies, and I'm mostly involved in the media informatics and the computer science master studies. At entertainment computing, these are the people who are actually teaching. It's not only myself, it's also Patrick Batzur and Daniel Martinek, who are very much involved in our teaching and also our research. So they are also quite on top of the game and really know what they're talking about. And both of them are, of course, avid gamers, as I have been in a previous life. So that explains the interest into the topic. And this is also, I think, a main takeaway that the big interest into the topic area is the best entrance point. So these are our courses related to computer games. We have at the bachelor and master level, we have electives. And so you can actually choose to take these courses or not. So these electives, you can, they are not mandatory, but they are quite popular. And in winter semester, we have a course called Gaming Technologies and Game Design. I will go into more detail about these courses later on. And in summer semester, we have the graphics-related courses, real-time computer graphics, real-time ray tracing, and cloud gaming. And then, of course, you can, at the end of your study, you have to write a thesis. And at the bachelor level, you have to write a thesis within one semester, within a practicum. And at the master level, you have to write a master thesis. But there is actually, there are courses before that. So you should run through the practicum 1 first, where you do some practical stuff, and then practicum 2 afterwards, and then a seminar, which I didn't put on the slide, and then you work on the master thesis. And of course, I advise a lot of these theses, which are really focused on the general top area of entertainment computing. And entertainment computing is not just games, it's a much broader area. But in our courses, in the main courses, what are the goals that we actually have? And maybe the biggest goal, or the overarching goal of all that we do, is you should be able to create your own game engine in C++ afterwards. So this is really one big, for me at least, this is one big requirement. So if you do all of these courses, then you should have a good understanding of how a game engine works, and you should be able to create your own game engines. And actually, as part of the courses, you're required to do that anyway. And our implementation language is C++. So modern C++, C++ 23 maybe. So this is really what we teach and where we want our students to be. And of course, all this can be split into various elements. So you should be able to have a good renderer. And for that, we have adopted the Vulkan API, which is, you have probably heard of, which is fairly new API for computer graphics. And you might also have heard that it's probably not the easiest one to learn, but we like challenges, and this is what we do. And then, of course, we have other topics like AI for computer games, machine learning, physics simulation, real-time physics simulation, networking and cloud gaming, real-time video distribution of games. So these are the topics, the general topics of our courses. Also, we have game design, which I will also mention, which is more like on the design and art stuff side. Yeah, and then you should be able to design entertainment games. You should be able to work in the game industry right off the bat. When you finish, you should be able to go there and be able to contribute. And also, you should be able to do research in games-related areas. And that is very important, for instance, also when you do a bachelor master thesis. So this is always part to do real research and not just any type of paper that you throw away afterwards. Of course, we cannot invent everything ourselves, so we use a lot of software that is available. Back in the day, many like 15, 20 years ago, we started with Ogre, a 3D, which you might have heard of, which is a C++ library, which is currently a little bit outdated, of course. And of course, later on, we switched to Unity along the way, Unreal. Some people use Unreal. Godot is now very popular. There are other rendering frameworks and open source game engines that are available and are very good, actually. But these are the most popular ones that students choose to use for their thesis, for instance. Nowadays, we also use a lot of machine learning libraries, of course, C++ and Python to drive the machine learning libraries. And also for teaching Vulkan, so in this very Vulkan-focused course, we use the Vulkan tutorial. I'll talk about this later on. On the other side, we have a lot of frameworks ourselves. And I think that is very important. If you want to teach stuff, you should have created these things in the first place by yourself. You should have some kind of idea what problems do you have? How can you solve problems? How can you achieve a lot of performance and so on? What are the biggest obstacles? And in this sense, we have created, or I have created myself, most of them, the Vienna Vulkan engine, which is simply a rendering framework for using Vulkan. I created that like 7 years ago. My colleagues have created the real-time ray tracing engine for their course. Then we have also created the Vienna physics engine for real-time physics simulation. Now we are booting up the game AI library, which should be like a collection of AI algorithms that are typically used in games. Currently, I'm finishing the Vienna entity component system, which is a very important part of modern games and game engines. Also, I will talk about the game job system, which I have been creating a couple of years ago. On top of that is a kind of a meta programming library, the type-list library. And one of my students has created within his master thesis the Vulkan video examples, which is also currently quite popular. You can find most of these on my GitHub if you're interested in it's like a little bit in flux, and sometimes I work on one of the projects and sometimes I work on others. But you get the idea that we try to provide a lot of code ourselves. So concerning the lectures themselves, I will now talk a little bit about the lectures. The first lecture that I will talk about is now in the winter semester going on. I'm on sabbatical, so I'm currently not involved in this, but usually I do this lecture. It's called Gaming Technologies. It has 4 semesters, 4 weekly hours. And it's split into a lecture part and a lab part where people are supposed to program like little snippets, little solutions, but also, and that is very important, they should, all of them have to program their own game project at the end. So a lot of these lectures have like the last, maybe 4th, they have time just to program their own game. And incorporating all of a lot of stuff that they have learned during the course of the lecture. And in this lecture, the topics are like these, real-time physics simulation. So how can you simulate a physical world? What are the algorithms? How can you get it to run in real time? And here we have a couple of topics. If you're interested into this area, you have probably heard of them before. We usually have something like a broad or narrow phase. The most important thing is to find objects that are actually touching each other. So this is the big overarching issue. And because you have potentially hundreds or thousands of, or even millions of pairs, you have to be very smart about it and have to very quickly reject pairs that are impossible to touch. Let's put it that way. And once you realize that they are touching each other, then you have to do something about it. So this is a physics simulation, and this is mostly about rigid bodies. We don't teach soft bodies yet, but we have implemented some stuff on that. Then we teach about AI for computer games, which is more like a traditional way to go about, which is a more deterministic way. So it's traditionally computer games don't use too much of machine learning, for instance, because it's non-deterministic and very, very complex to set things up. So we teach these deterministic algorithms more or less. And then finally, I do talk about parallelism and multi-threading in game engines, data orientation, so cache optimality, locality, job systems, and so on. And then people are supposed to create their own game. If you're interested in this part, for instance, job system, you can watch my CPPCon 21 talk about job systems in game engines and about the game job system that I created, which used coroutines. So coroutines are really a core part of that, because it turns out that coroutines are very nice to be used in a job system. Now, people are supposed to do these tasks, so they're bi-weekly tasks, roughly. These are some tasks, for instance, that we had a year ago. Solve something in mathematics, compile it in a Vulkan engine, compile a physics engine, play around with gravity, and then implement a new broad phase and collision shapes and things like that. So these are all small snippets that they should solve, and then at the end, they should come up with their own game. How do these games look like? So here, these are actually games from last gaming technologies. So they have some kind of physics or AI involved. So here we have CubeMania, for instance, which, is it already running? So I never know how this actually works. So yeah, so this is a kind of a duck that can lay eggs, and when the eggs explode, they can actually kill all the opponents, and they can brush away all these obstacles, and then you can go out on the other side. And here, this is also quite a nice game. So obviously, the embedded videos doesn't work here, so it doesn't matter. So these are a couple of examples where they used also the physics engine, or they come up with their own solutions, and the Vulkan engine. Now it's something is good. Okay. So now, okay, so you can lay an egg, and then it explodes, and you can kill away your opponents. And this is the sphere spider, where you can you're hassled by these cubes and then shoot at them and try to avoid. Okay, one of the basics of this course is the Vienna Vulkan engine, so people are supposed to use it simply because it was tailor-made for these courses. For instance, if you use Unity or Unreal or Godot, they come with their own physics engine. It doesn't make much sense to learn how to use one specific engine. It makes more sense to be able to implement your own, and that's why we actually prefer to use not a game engine that you can get one of these big ones, but you're really focusing on implementing your own stuff. So on the left, we have the current version. It's a bit outdated. It's basically a rendering framework with the Vulkan API, and it uses GLSL, GLM, GLFW, async, nuclear, BMA, if you know what this means. Currently, I'm actually working on the second versions, and I'm trying to go away from some of these frameworks. And the idea is to use what is actually distributed with the Vulkan SDK anyway. And if you download the Vulkan SDK, for instance, you have SDL2, you have VMA, you have Vulk as a function loader. So all of these things are already in the SDK. So there is no reason to use, for instance, GLFW, for instance, because SDL2 is already there, or use your own function loader because Vulk is already there. So also there will be some updates. Perhaps one of the biggest also will be the new shader language that's coming out, Slang, which is an update of HLSL, kind of, from NVIDIA. So this is really the future. And so I really want to go away from GLSL, which is really outdated. And you can really see that it's outdated, and going to Slang, which is like the next step forward. And of course, going to the entity component system and a more decoupled engine architecture. So actually, I wanted to have a demo. Let's try that. So how does that look like? So I'm starting on. So this is the demo game of the engine, which is not very complex. You have to. No, of course not. Of course not. Okay. Okay, I have to move it to the other side. All right. Okay, now we are talking. So you have to catch all the boxes, and you have a couple of seconds left. And if you catch 10 of them, then you get an extension. So that's a fairly easy game. And I just want to show you the amount of code that is actually necessary for that. So the amount of code is actually this. So this is just having your own game engine class. So this just loads the scene, all of these assets from this. So this is not very interesting. Then we have something that creates the graphical user interface, the window on the left, also not very big, and the whole game is actually this. Okay, so that's as easy as it gets if you use this engine to have a very simple game like that. And it's not about having super complicated games, but really implementing your own stuff that makes it more interesting. Concerning the physics engine, this is also in my GitHub, and it's for real-time physics simulation in games. As I said, it's about rigid bodies, but we also have soft bodies, and we also have many constraints that are implemented, like ball socket constraints, hinge, angle limits, motors, sliders, fixed constraints, and so on. You can play around with it. And for the time being, it's actually engine agnostic. It doesn't rely on any engine because you can just register some callbacks, and then you can talk to your engine via the callbacks. You can combine it for single or double precision. For me, quite interesting was that single precision is totally fine, even if you have hundreds of objects. So the numerical accuracy of single precision is totally fine. And I want to give you also a little bit of a demo here. Starting it up. Is it working? I don't know why this takes so long. Laptop is doing a lot of stuff, obviously, right? But, you know. Yeah. Okay, so again, we are in this world, and now we can do some stuff. For instance, we can. Oops. Something is really not working now. Okay, let's try this one. So stable stacking. So I've never seen this, I guarantee. Never seen this. Okay, so on this screen it works, and on this screen it doesn't. Okay, so this is a zoom effect. Oh no, no, it does. Oh, no. Okay, so let's make a pyramid. I think the CPU is a bit is struggling because of the zoom. Okay, so yeah, so zoom is retake. It runs on the CPU, and so the CPU is currently struggling with that. Okay, yeah. So yeah, the laptop has too much to do now. But what we can do is we can show a video. No, we can't. Oh no, it doesn't. Let's go on. Yeah, so it's CPU bound, and therefore the zoom is obviously taking away too much CPU from this laptop. Okay, so yeah, so usually what you can do is you can create these stackings. You can destroy them by shooting stuff into them. You can create motors and machines and so on. Okay, so let's moving on. The next lecture that we are having is game design. So this is not very technical, and here people also can use a game engine from wherever they want. And this is really just about game design. So this is how what do you have to do in order to create an interesting game? What do you do in order to have a successful game project, a commercial project? And so here we have the topics, for instance, talking about game engines, roles and in game design documents, prototyping, about the player interest curves and keeping players occupied, serious games, obviously balancing performance and so on. So this is really just how to design interesting, engaging games. In the summer, we have the more computer graphics focused lectures. So this is called real-time computer graphics. And this is really focusing on the Vulkan API. So if you're interested in Vulkan, this is one of the few courses in the world that actually teaches that. And it's so rare that I was very surprised. This year I was in Sunnyvale at Google, and they told me they don't have people from Samsung and Qualcomm told me they would like to teach their engineers about Vulkan, but they don't have courses for that. So currently they're actually using the videos from this course are used by Samsung, Google Android Studio, and Qualcomm to teach their own engineers. So, and a big part of obviously is about just the Vulkan API, which is extensive and which is really requires a very steep learning curve. But it's all of the courses that you've seen and that you will see, they are really very much focused, maybe with the exception of game design, they're really focused on Vulkan. So it's not just this course where you learn Vulkan. You can use Vulkan and you will use Vulkan in all of these courses. So when you walk out of the study and you have done all of these lectures, you will have a good understanding about the Vulkan API. And that is what the gaming industry and also all of these companies are really looking for because it's such a steep learning curve. So here we have all the topics, at least not all of them because it's too much. But if you go through these topics, you are able to create your own renderer easily. So that's the idea. So like devices, queues, swap chains, synchronization, render passes, frame buffers, and so on. So that's very extensive. This course actually tries to teach you what is in the Vulkan tutorial. The Vulkan tutorial comes in different versions, but it's just like the minimum work you have to do in order to render something. And the minimum work you have to do is 1,500 lines of code just to render this. Okay, load one object, render it. Okay, so this is extensive. And you might think that this is crazy, and in some way it is, but it's a low level just on the bare metal API. So what you're actually supposed to do is you create your own device driver and a device driver abstraction. So you have to create all of these things that I've shown on the previous slide in some synchronized way, and then you are able to talk to the device in an optimal and high performance fashion. But in order to go into there, that is a high, that's quite a big step, let's put it that way. I took this Vulkan tutorial and changed it in order to use it to make it more accessible. So I switched the FW to SDL2. I introduced also ImGUI. You probably have heard of that. This is this GUI framework here. I introduced Vulk, the function loader, and VMA, because the tutorial doesn't use any of this. And I changed all the functions to pure functions, so they just get input and output parameters, but they're not using a shared state. Because if you have this amount of code and they're all working on the same shared state, then you can very easily get lost of what's happening. This is currently the version, and it's very easy. And also, if you're interested in creating your own renderer or your own game engine, it's very easy to use pure functions because you just plug and play. You take them, put them in your engine, and then there are no side effects. You give it parameters. They will create a pipeline for you. They will create a device for you. They will create synchronization constructs for you without any side effects. And that is very, very useful. Again, we have a couple of lab assignments, which are all centered around this Vulkan tutorial. So do stuff in the Vulkan tutorial, like change the source code slightly, create another descriptor set, create another pipeline, load more objects, and so on. So in the end, you really have a good feeling of what's happening in the Vulkan tutorial. And once you know that, you can take all these functions and put them in your own renderer, and then you're good to go. But of course, it's a lot of work. And I think that's the key takeaway. If you look at the topics list, this is a lot of work. And learning Vulkan is a steep learning curve. It's not something you can do within a weekend or within 2 weeks or within a month or within 2 months. No chance, okay? So this is really, really a lot of work, programming, and experimenting with stuff. So this is how a lecture looks like. Typical slides. I show how to create surfaces, for instance. Surfaces, then the interface between the Vulkan and your windowing system. You can query surfaces around the format and the swap chain that they support. Present modes here. And once I'm done with that, I fire up my IDE and then debug through the tutorial and say, okay, here we create the surface, and here we query different present modes, and here we create the surface, and so on. So that students actually see where in the code is this happening. And once you have a good feeling about where in the code this is happening, you can really you have a mental model of the whole tutorial. So I've been doing this for quite a long time. Vulkan isn't that new. It started around 2016, 17, and I was very early on adopting it because I came from DirectX, and then DirectX 12 came along, which was totally different to DirectX 11. And I thought, okay, DirectX is very much glued on Windows. And then Vulkan came along, and it's multi-platform. And I thought, okay, yeah, that's it. how difficult can it be? Well, very difficult. And so these are my takeaways from like getting into the Vulkan tutorial and trying to really teach it in a university course. So it's a massive work. If you want to learn it, you're learning it from scratch because there's nothing like it before. And making an engine and your own render is really a good investment. It's a huge challenge. It takes months and months. So it took me like 4 months to do that. And the engine wasn't the best engine, but it works. What more can you say? I do record all the lectures, and I try to bring all the students to the same level at the start, so talking about mathematical background and so on. But overall, it's a huge amount of context that should be taught within a course, and that is a big challenge because you can't just say, okay, I just cut it in half. That's not going to work. You have to teach like 90%. There are some things you can leave away, like queries. You can use queries, but they're not really necessary. But otherwise, like 90–95%, you have to teach. Otherwise, you don't know what you're actually doing. Also, it comes with different interfaces, C++. Industry like C++, but it's also another level of complication. It's still in flux and it's still ongoing. And of course, Vulkan is evolving with a breathtaking speed. And of course, looking at the students, how they are actually doing, there's a great interest in the game-related courses, of course, and students are really heterogeneous in what they bring to the table. So there are a couple of differences in mathematical skills. So for instance, so it's good to give them the same like light head start at like this linear algebra and reference frames and so on. But afterwards, I can say that they really know the Vulkan tutorial, which means they know the parts of the API that are really necessary to create their own renderers. And it's highly motivating to program games at the end. So this is really a big, one of the big motivators is at the end of the course, everybody shows their games, and then it's very surprising and a lot of fun to see that. We have other courses, of course. So here we have the lecture real-time ray tracing. So the previous one was about rasterizing, about using the typical rasterizing pipeline. This is now about ray tracing because Vulkan also has its ray tracing pipeline. We have implemented, my colleagues have implemented the real-time ray tracing engines just for that. And it's very, very similar to what I've been doing. So it's C++20, SDL2, obviously, IMGUI, yes. This is where you go to GLF2. I still have to go there. And then they use a mixture of a deferred renderer, and then parts of what they do is ray traced. So usually you don't use a ray tracer for all the scene, but you have one shot, and then above that, then you can ray trace reflections and shadows, for instance, and refractions. And here we have a couple of topics, and at the end, there's a heavy part also on machine learning, because machine learning is really the future for real-time rendering. So it's really something that is not even still at the horizon, but it's already here. So post-processing, machine learning post-processing is a big topic now, and it will take over at some point. So it makes sense to really lay the path also there. Yeah, and finally, we have, as a final lecture, cloud gaming, which is more about real-time video. So people are learning about the basics of video encoding. How does encoder work? H264, H265, H266. Then we use FFmpeg, and in the future, we will also use the Vulkan video encoder. And then, so we make a screenshot and then encode the screenshot and send it to a client. So the server and a client, and everybody is supposed to create their own cloud gaming solution. So that consists of a server that's running the game and a client that's just presenting the output, collecting user feedback and sending it back to the server. So you have a closed control loop, and you're remotely steering this game. So this is about GUI frameworks, audio, And a lot of networking, obviously, real-time networking, buffer dynamics, which is very important here, low latency, also low latency video encoding. So this is also in summer then. Last but not least, I have a big focus on thesis that I supervise. In summer, I had over 32 theses that I supervised, which are on many levels. They started at a practicum level, bachelor, master level, and also PhDs. I have a big list of topics. You are welcome to have a look at them. And my students should pick one of them for their thesis. The reason for this is that these topics are guaranteed to have all the substance that you would expect from a thesis, like from a bachelor and master thesis. They're supposed to be scientific works, and therefore there should be some kind of innovation. It's an open question that the students should solve. And also it should be possible to send them to an international conference at some point. So not all of them will cut them reach this cutoff value, obviously, but many of them do actually, and we'll come to this later on. So you have a couple of example topics. For instance, here, stiff soft bodies, like modeling more like soft bodies, like a wobbly something for the Vienna physics engine, which is not yet implemented. Realistic limb, skin, and muscle model. SpaceX, like rocket landing, just we create a physics version for that. That would be a good bachelor thesis, for instance, and so on and so on. So the list is quite extensive. Here we have a couple of bachelor's and master's topics that I had. So this was in 2023. This student created a Vulkan, the graphical Vulkan editor. One of the big things about Vulkan is the code vomiting. So you have to create a lot of code, like thousands of lines of code, just to create something and have a look at it. And the idea was to have a kind of an editor where you just click together your pipeline. So creating pipelines are the biggest objects in Vulkan. So the big fat objects, and they kind of store all the state of renderer. And here you just click it together what you want, and then you can show it in this window. And when you're done with it, you can save it, and it will save all the source code. So you're not really you don't have to create the source code. You just use the editor, and the editor creates the source code for you. So this is something that I'm still working on. So this was the first shot, but it worked quite nicely, but we're not there yet. Here, another master's topic, going to the Vienna Vulkan engine, and the student implemented 3 more renderers, a deferred renderer and 2 different ray tracing renderers. And then he looked at the performance, for instance. At the time, there were different extensions. There was the initial NVIDIA extension, and then Kronos adopted it. It was not 100% the same. So there were some differences, and the students tried to evaluate what's actually the difference in performance. So trying to bring bachelor and master thesis to international conferences, this is the output for 3 years. These are all bachelor and master's papers, all of them. None of these papers have been written with PhD students. I have PhD students, they publish themselves. This is bachelor and master thesis. Okay? So this is really my focus right now. I try to bring my students, even from the bachelor level, to an international conference. So Lukas Petsai, this was a bachelor thesis. Ralf Dworzansky, master thesis. Campisi, bachelor thesis, master thesis, bachelor thesis. Okay? So the idea is really to have something of substance, a topic that is really innovative, where they try to find a good solution, and then have an innovative and new solution, and then we can try to submit it. Of course, lots of what we submit is also rejected. Like yesterday, one of us rejected, so bad luck. We will resubmit it, and finally somebody will accept it. So here, this is Christina Lalic. She was at a Sega conference in Madeira and presented her master thesis as a paper, for instance. And this is me with Bernhard Schrenk, who is a master student, and we presented our work at this year's Vulkanize conference, which is more like an industry conference. It's not a scientific conference, but nevertheless, it's actually a very interesting conference. And it was very important to go there because this is where you learn the new areas and the new directions of Vulkan. Where is Vulkan going? So I don't want to teach stuff that is completely outdated. So, and Bernhard, he's an exceptional student, and he's now creating his own game engines. And he's also created these video extensions very early on, 1 year before they were released, actually. If you're interested into his journey, have a watch the video of our presentation. It's quite entertaining because he described how he suffered through all the process. Yeah, that's, and his master thesis is really doing something that was quite unique, in fact. Okay, what are the outlooks of the next years? Because the next years will bring a lot of changes. Of course, I'm personally focusing on the next iterations of the engines, rewriting the Vulkan engine, then rewriting the physics engine because it's more or less a mess, to be honest. But also focusing on more rendering techniques like 2D post-processing with generative AI. So this is really coming. This is really a big topic. Already students are really on this topic and working on this topic. But I want to bring it into the engines and make it accessible also. Using more LLMs, of course. We are using this now also in our thesis, but this is really coming. World building. And I want to stop my talk by showing you a bachelor thesis output from Manuel Zechmann. And hopefully this works. So he took some templates that he found, very, very good templates, and he implemented it in Godot, in the Godot engine, because Godot doesn't have that currently. It's a completely procedurally generated planet, and that was the idea. So you want to create something like No Man's Sky, for instance, which is better than that, obviously. But this is the first step of having something that looks really beautiful. And as I said, he didn't invent all these techniques, he just implemented it in Godot for his bachelor thesis. Let's have a look at this concludes my talk. Thanks for listening. And any questions?
15 minutes for questions. Teaching the Vulkan, what kind of lecture will you give here?
Yes,
okay,
yes. Absolutely. Yeah. Absolutely. So that has always been a big problem. If you teach DirectX, for instance, it's really glued on Windows. And that's OpenGL is very legacy stuff, so it's very outdated in some way. And when Vulkan came along, it was like the solution, but it was a solution with a caveat, the steep learning curve and the huge amount that you have to learn. But now it's multi-platform, so you can do it on Linux, you can do it on Windows, you can do it on Mac even, on Android. Yeah. So we support Windows. Linux is very easy. Mm-hmm. Mac is a problem. Yeah, so we cannot support all of this. Okay.
But if they support tutors that assist you? Or?
Yeah. We have tutor who will help. We have previous solutions that we can show. There's tons of explanations in the web, like how you set it up on Mac. theoretically, it's not that difficult, but of course, everybody has a different MacBook. You can have a very old MacBook, which is with outdated integrated graphics, which are insanely bad. And the more modern MacBooks, and they are very good, and they can easily run that. So the range of Macs and what they can do graphically is perhaps the biggest problem. Well, we use generative AI mostly in the thesis, like bachelor thesis, master thesis, not yet in the computer graphics courses, because there's simply also not enough time, because there's not enough space for these topics. And usually, no, that's not possible. So the tasks are really, they're either based on the Vulkan tutorial, or you should use the Vulkan engine. And you can see this, right? And of course, at the end, they have to show the source code and explain what they've been doing. So that's
training that assignment, the basic C is basic C exercises.
Yeah. So it's yeah, they have to deliver a solution for a specific problem, and if they do, they get the points. And of course, if they miss it, or it's not exactly what was asked of them, then they lose some points.
In your experience, what do students struggle most? What do students struggle most with? Is it the basic get the graphics on the screen? Is it the physics API? What is hardest for them?
What is the hardest for them? I think the hardest by far is learning the Vulkan API, because it's basically 90% or nothing. You can forget about it, and it's not so that each part of the Vulkan API is not overly complex, but you have to learn all of it and understand what it's for, and understand when you have to use it and how you have to program it. And if you try to start by programming from scratch, like you start with an empty project and you start typing all this, you will not succeed. No chance. No chance. Okay, you start with something that works, and then you transform it to where you want it to be. Because you can just one simple problem, one simple mistake, one parameter wrong, and you don't see anything. Right. And we're talking about 1,500 lines of code or more. Find the error. Good luck with that. Okay. Yeah.
This is now coming with my security hat on, because C and C++ is we're trying to verify how much are other languages gaining importance for game development. I mean, I understand we down to level and get the last step of performance and get the C++, but for our embedded systems programming, we try to develop as much as we can to us. Does that have a place in game development for?
There are Rust engines, yeah. There are Rust engines, yes. The point with C and C++ is that it's a zero overhead program language.
That's why.
Yeah. It's gaining traction. Yes, it's implemented in a Linux kernel, so there are game engines using it already, but they are like isolated. The point is this: that every major game engine is implemented in C++. Everyone.
There are no good wrappers around Vulkan.
I'm sure that there are Rust bindings. I'm pretty sure about that. The point is, why bother with yet another language? Okay, so we have seen Go, Swift, Rust. So they come and then they go. And I mean, you can jump on the new bandwagon and hope for the best. But C++ is dominating in game engine development still. And I have to say that C++ 20 or 23 are completely different languages than 0, for instance. C++ 3 these are different languages. They look differently. So you have all these lambdas and these templates programming, and you have folding expressions and meta programming, and you have an SDL library that is really very safe to use. Probably it's not the most best performance. So yeah, I understand that from a safety perspective. However, and maybe that's the biggest issue here. This is a game engine, okay? So if it crashes, a 14-year-old kid will cry, okay? But nobody will be hurt. No car will crash. No plane will crash. In a game, what you do is you even don't want any exceptions. So in a game engine, you switch off exceptions because they just eat up performance for nothing. You debug, and when it's debugged, you ship it. You know. Well,
So you don't.
It's debugged. Okay, it's already debugged, so it's not supposed to crash. So that's the big issue. A game is enclosed. It's like it's running in a bubble. Okay, so there it's not really attached to the rest of all. I mean, you have a multiplayer game, and then you have bubbles which are attached to each other. But it's not like this is like an open system that is talking to everyone, and then suddenly you get crazy data in. That's not happening in a game. Usually a game is not a server that you could actually reach. A game will reach a server, but not the other way around. So it's not a game engine. A game is not waiting for others to like. Yes, you can have a multiplayer game, but if you keep the interfaces very narrow and really restrict what they can do, I don't see a big issue here actually. Yeah. So like Vulkan is a good example. Vulkan has a layered structure. Okay. So during development, you switch on the layers and you have very rich debugging features. So if you do something that's not allowed, like you want to destroy an object that has not been created, or you want to destroy it twice, or you want to a parameter is not allowed, the debugging layer will print an output. It will tell you about it. But once you're done, you simply switch off the layers, and they're gone. They're simply gone. It's like an assert, yeah. And then it's supposed to run without bugs.
Take questions.
Yeah.
The first one is related to publications. Do your students have to publish full papers, or do they rather publish work in progress papers?
It's when the thesis is finished and submitted, we make a paper out of it. That's it. So then we try. And
the question was from me in the Zoom. Can you hear me?
Yeah.
Yeah. Because I also try to do this with my students, that once they've finished their bachelor's or master thesis, I try to make or write papers with them. But most of the time for a bachelor's thesis, we do not succeed to write a full paper with 10 pages or something like that. So we typically have to go for a 4 to 6 page work in progress paper. For master thesis, it's often a bit easier to make a full paper, and that's the area where I wanted to ask you about your experience, how hard it is to make a full paper out of a thesis with your works.
It's very hard. So it's because it's more or less a random process. We all know that paper reviews and acceptance is at some level it's a random output. So, and I wouldn't really overstress the importance that it really gets accepted. Some are getting accepted as a short paper, some are accepted as a poster, and some are accepted as a full paper. And yes, we have bachelor thesis is, for us, it's 25 to 30 pages. And of course, then you have related work, introduction related work. And at some point, students also write into this, how did I implement it? What classes did I use? We take that and throw it out. And the rest is the paper. Okay, because the rest is the scientific part. Yeah, it happens. It's random. And I think it also depends. You have to adhere to the scientific standards. you have to carry out, for instance, a lot of times we do studies with participants. So that is a staple, that is a fixed staple for many theses, not 100%, but like 80%. So you really have to come up with scientific evidence that what you have been doing is actually working. So for instance, the planet work from Manuel Zechmann, he's doing studies with participants. Kristina Lalic, who presented the poster, she did a study with participants. So it's not about just writing the software. You have to clearly state a hypothesis, research questions, and then do all the work from A to Z to come up with good evidence what you have been doing actually works. And then there is a random chance that it will be accepted or not. And I think also the topic is very important. So come up with good topics.
Probably I may add one follow-up question to this. And the question is, if you get not accepted, do you keep your students in the loop, or do you try to republish them yourself at some other venue? So their bachelor thesis has been completed. Do you keep them working somehow on the paper until it is finished?
Usually I invite them. I make them an offer. If the paper gets accepted, I will pay you the travel. You know, I will pay for that. I have fundings. I'm funding the whole travel, travel costs, conference costs, the hotel costs, and for many of them this is very attractive. So they gladly turn their thesis into a paper, which is not that much work actually. And then we submit it, and when it is accepted, they go there and present it. So for instance, in December, I will present a paper, a master's topic, because the student doesn't have time. And another paper in the same week, another student will present his bachelor thesis in Coimbra. I think this was also at a conference. So yeah, this is a master's thesis. So these are two master's theses, and this student will present the paper himself because he's interested. And here the student doesn't have time, so I will present it for him. But usually they are really interested. So like here, the student went there to Los Angeles, and also the second student also. It's the same conference, and both students went there, and I paid for the travel, which is of course restricted by the funding that you have. But it's a good incentive. Kristina Lalic also presented her work at Madeira also. So having funding and sending them is a good incentive and good motivator to. So they actually go the extra mile and create the paper and submit it. And more often than not, it's not accepted. So what? So you send it to somewhere else.
And you said you test a lot. Where do you find your testers?
Usually it really depends on the level. If it's a bachelor thesis, I do not require more than 10, for instance, participants. Usually I ask them, do you have friends? Do you have colleagues that you can ask? Relatives, of course. And for master thesis, maybe the target would be 20 participants. And for PhD, of course, it's much higher, because then we're really going into a domain of high scientific validity. So depends on, but nevertheless, you try to get it published anyway.
Thank you very much for the answers. Thanks.
Thanks.
One quick question.
Sure.
Is playtesting also part of the courses?
It's perhaps in game design, yes, but it's part of the. Yes.
Well, of course, your students, if they do not go to the University of Vienna, they then go to industry. They can go to the gaming sector, but they also other sectors where what they have learned with you.
Usually they go anywhere. So they go to gaming studios also, but they also mainly go to industry. And interestingly enough, most of them already have a job. So if I have a master's student, she or he already has a job. So that's like 99% for sure. And sometimes I see people who change jobs, but usually they already have a job. So it's not really depending on what they're doing. It's interesting for many of them. And because they have jobs, they're working in industry, they're working as a web designer, as a web programmer, as a embedded systems programmer. One of these students is working as embedded systems programmer, for instance. When they tell me they're very good in programming. Bernard Schrenk is an exceptional programmer for many years, and he's working for a company. So they are really already very good in programming, many of them, and so they usually keep their job afterwards.
All right. Thank you very much.
Thank you. Oh.